first thing that we're going to talk about is local linearity and linearization, which is basically a fancy way of saying we are, again, finding equations of tangent lines, but we're going to look at a point that's really close to that specific tangent point so that we can approximate a value, okay? So we're going to basically look at the value of a curve using our equation of a tangent line. That's what we're going to come out from solving these. So if you look at this picture on the left here, if you look at it just kind of quickly, it looks like what? It looks like a circle, right? But if you look at it closely, very closely, there is actually 24 sides on this polygon, which, fun fact, is this word right here. How do you say it? I have no idea how to say it, but it's something like that. So, fun fact, it's a thing. Look it up on the internet. It does exist. When the number of sides are this large, the lengths become smaller and smaller, right? So in calculus, a lot of the times we're talking about limits. As we approach some number, that number a lot of the times is infinity. As we go to infinity, what is happening to our function? Or if we look at this kind of circle idea, if we have our number of sides approach infinity, so if our number of sides are super, super large, that means it's going to get closer and closer and closer to looking like a circle, right? So that means the side lengths are approaching 0. So sometimes you see curves in the real world, right? We see these side rails if you ever go traveling in the mountains and things. If you look at them actually very closely, though, they're not actually curved. They're actually just like straight guardrails, right, that create a curve. Same thing for your wooden, or not just wooden, but your roller coasters. A lot of the times they are going to be straight lines instead of actual curves because it's just it's easier and it's cheaper to make them that way. So yeah, we're going to look at tangent lines on curves and approximate values near them. So we've got this fancy formula here. This picture should look kind of familiar because we used it again when we were talking about tangent lines originally, how to write equations of tangent lines. And this formula right here is nothing super crazy. It's just point slope form, but using different notation. So anytime you see this L of X formula or this L of X notation, L of X stands for your linear approximation. Which technically, it's my y value. If you look at my picture here, L of X is equal to y. So this is technically y minus my f of a, and my a point is just this point on the curve right here that the tangent line is going through. So this is also just like an x and a y value, right? That's my x1 and my y1. So in my formula, I've got y minus y1 is equal to, what does this notation f prime of a tell me about my line? That's my slope, right? So my slope times x minus x1. That's all it is. It's just written with different notation in terms of the picture that we were given for our our linear approximation. What is the difference between the first equation here and the second equation?
One is already isolated.
Yeah, that's exactly right. So I'm isolating this linearization, right? So I'm isolating L of X. So all I did was add over the f of a. So this is technically your y is equal to y1 plus m times x minus x1. So we're going to find the equation of that tangent line. So again, in this picture, we're going to find the equation of this tangent line. And then the local linear approximation allows us to figure out, okay, what is that point approximate to? That point in red that I approximated is really close to being on that tangent line, right, on that curve, but it's not exactly on that point on that tangent line. So basically taking some derivatives, writing some equations of tangent lines, we're going to be able to find what those values are without using a calculator, okay? All right, let's move on to an example here. First one, I've got, use the linear approximation for f of x is equal to the cube root of x at x equals 8 to approximate the cube root of 8.1. Now, what does the cube root of 8 equal? 2. So like in our brains, we can probably approximate the cube root of 8 is going to be really close to 2. 2 and some type of change, right? So we can also do this showing with a derivative. So I'm going to first take the derivative of f of x. So f prime of x is equal to, we can rewrite this as x to the 1/3 power, right? So take the derivative of that using my power rule. I would have 1/3 x to the negative 2/3 power, right? Which could I rewrite this as 1/3 times the cube root of x squared? Is that the same thing? Yeah, and I think we'll do that because like this would be a problem that you would not have to use a calculator for. So it'd be easier to evaluate it if we wrote it in this format, because at least for my brain, it works to make more sense if I take the cube root of something and then square it versus taking it to the 2/3 power. That's a little hard for my brain to work. So now I'm going to plug in 8. So f prime of 8 is going to be 1/3 times the cube root of 8 squared. So evaluating this, I would get 1/3 times 2 squared, which is 1/12. Okay, so that right there, 1/12 is what for my tangent line? That is my slope. Okay, if we're writing an equation of a tangent line at the point x equals 8, I have an x value, I need to find a y value. So how am I going to find a y value? Plug it in to this formula here. So if I'm finding a y value, f of 8 is equal to the cube root of 8. So in this case, my y value is equal to 2. So your point that you're going to use in your equation is going to be 8, 2. And now we can write the equation of a tangent line using those two things. So I've got y minus y1, which is 2, is equal to 1/12 times x minus 8. This part is nothing new. We've found equations of tangent lines before. And now here comes the new part. Any questions up to this point? Okay, so local linearization, local linear approximation, same thing, okay? We're gonna simplify this so that y is all by itself on the left-hand side. So L of x is equal to 2 plus 1/12 times x minus 8. Okay, y and L of x in this case, those are the same thing. What is the approximation of our line at that point where x is equal to 8? Okay, well, we're specifically looking at the cube root of 8.1. So technically, I'm going to approximate, using my formula, the linear approximation formula, I'm going to approximate when my x value equals 8.1. So that's where the place of the x is, right? So we're going to use the local approximation, or the linear approximation. L of 8.1 is equal to 2 plus 1/12 times 8.1 minus 8. And now we can approximate this. If I simplify this, this is something that we could do without a calculator. 2 plus 1/12, and I'm going to write this next one in parentheses in a fraction form. 8.1 minus 8 would just be 1/10, right? Or 0.1. Because now I can multiply those together. Multiply two fractions is going to give me 1 over what? Yeah, 1 over 120. So I've got 2 plus 1 over 120, which just gives me 2 and 1 over 120. So that is my approximation at 8.1. So that's my y value when my x value is 8.1, the approximation. So like on our picture here, this is when it's equal to 8. 8.1 is really, really close to that. So that y value would be at 2 and some change. 2 and 1 over 120. Okay, but that's an approximation. It's not the exact value. If I wanted to find the exact value, I could plug this in my calculator, right? Okay. All right. Now these next two, we're still going to do that local linearization, but we are going to have to to find the error in between things. So think to your science classes. How do I find the error between values usually? The actual minus the theoretical, right? And I'm not talking about the percentage. I'm just talking about like what is the actual change, like what is the error between two values. So I'm not finding the percentage, I'm just finding the error. So example 2 here, we are going to find the error first, we are going to find the linear approximation first of this function, f of x equals e to the x at x equals 0, and we are approximating it when we've got the 4th root of e. Well, this is also the same thing as e to the 1/4 power, right? So technically, I'm looking at the end, like when I plugged in 8.1, I'm going to plug in x is equal to 1/4. That's what I'm trying to approximate, okay? But first, we got to find the derivative. So derivative of my function, e to the x is equal to e to the x. I'm writing a tangent line, I need the slope, specifically at that point of 0. So f prime of 0 is equal to e to the 0, which is just 1. Anything to the 0 power is 1. So my slope is 1. Now my point, I have an x value is 0. How do I find my y value? Plug it in, right? So f of 0 is equal to also e to the 0 in this case, which is 1. So my point is 0, 1. My slope is 1. So if I wrote my formula, I'd have y minus 1 is equal to 1 times x minus 0. Okay, so my linear approximation, again, your y is the same thing as your linear approximation. So L of x is equal to 1 plus x. Those are the same thing here. We're looking at when I plug in an x value, what is the approximation of the y value going to be output wise? So I've got my linear approximation formula. Now I want to evaluate it at when my x is equal to 1/4. So I'm finding L of 1/4. When I plug in 1/4 to this formula, I get 1.25. So my linear approximation of x equaling 1/4 is 1.25. So at a point of 0.25, 1.25. Okay, again, notice how I did not plug in the 4th root of e here. I did not plug in the 4th root of e. I plugged in 1/4 because that's where the x is. The x is up here, so the exponent would be 1/4 in this case. Okay. So now here's where the error piece comes in. So error is going to be equal to your actual value minus your estimated value, or your theoretical value, the one that we found using my estimate or my approximation. So here's where the actual calculator piece comes in. In your calculator, I want you to take the 4th root of e and subtract 1.25. What are you going to end up with approximately? What are we ending up with when I plug that in? 0.034. So what that is saying, right, is that the actual value of the 4th root of e is 0.034 more than what our approximation was. Okay? Our approximation is obviously not going to be the exact value, but it gets us pretty dang close. Okay? All right. Last one here. We've got a tangent line to the function f of x is equal to x squared minus 3x plus 5 at x equals 4. And then we'll talk about what the rest of that stuff means here in a minute. But what I want you guys to do right now is find your tangent line to this function when x equals 4. So kind of do those first 4 steps there. Figure out what is your tangent line equation, what is your linear approximation equation, and then we'll talk about what the rest of that error stuff means here in a minute. I'm going to start showing my work here. If you aren't sure what you're doing, you can follow along. Okay, so I found my point, I found my slope 5, and then 4 comma 9. And now I can write my equation of my line. So y minus 9 is equal to 5 times x minus 4. Do we all get that? Yep, perfect. And then our linearization would be L of x is equal to 9 plus 5 times x minus 4. Okay, that is my linear approximation formula of the tangent line to that point at 4. And now where the tricky part comes in a little bit here is it's asking us, when is the error going to be at most 0.1? At most meaning what? Can it be bigger? Can it be less than? It can be less than or equal to, right? So we're thinking, when is this going to be less than or equal to 0.1 when we are approximating f of 4 plus h. We're going to find the range of values that we can plug in for h that would actually give us an error of at most 0.1. So in order to do that, error, again, is your actual minus your approximation, right? So error, let's just write that out, not in highlighter though. Error is my actual minus my estimated or approximated. So the actual that I'm plugging in, that's going to be my f of x, or not x, f of 4 plus h. So what does f of 4 plus h evaluate to? We'll figure that out here in a second. And then I'm subtracting my approximate, or approximated, which is L of 4 plus h. And that is going to be, when is it less than or equal to 0.1? We're trying to figure out when is my error less than or equal to that, for what value of h, okay? So I'm going to kind of work some of this stuff off to the side here. I'm going to do L of 4 plus h first, just because my formula is right there. So L of 4 plus h means I'm going to plug in 4 plus h anytime I see what? An x. So I've got 9 plus 5 times 4 plus h minus 4. Which means those 4's inside the parentheses are going to go away. And I'm going to be left with 9 plus 5 times h, right? So that is my local approximation of 4 plus h, which means I'm going to plug this in where I have my approximation or my estimate value for my error, okay? But now I need to find also f of 4 plus h. F of 4 plus h means I'm going to use my original formula up here, and anytime I see x, I'm plugging in 4 plus h, right? So I'm going to have 4 plus h squared minus 3 times 4 plus h plus 5. So I can do some simplifying here. If I simplify this on the right-hand side, 4 plus h squared, that would give me h squared plus 8h plus 16. Distribute that negative 3, so minus 12 minus 3h plus 5. Combine all those like terms. H squared plus, how many h's? 5 h's. And then add all those numbers together here, I get plus 9. So f of 4 plus h is equal to that whole thing right there. So I'm going to plug that in to where my actual function is equal to. So let's go ahead and do that. In my absolute value here, I've got h squared plus 5h plus 9 minus, parentheses are important, 9 plus 5h. what's going to happen inside those absolute values? Well, yes, it's always going to be positive, but like, what am I going to simplify to here? If I distribute that negative, I just have h squared, right? If I distribute the negative to the 9 into the 5h, then that means all of these are going to go away. So I'm just left with the absolute value of h squared is less than or equal to 0.1. How do I solve this? Square root, both sides, and I'm left with h being less than or equal to the square root of 0.1, which if you plug that in your calculator, you get 0.316. However, since it's absolute value, could I plug in negative values as well? And also it's squared, right? So I need to account for the negative side as well. So negative 0.316 all the way up to 0.316 are going to be all of the values for h that you can plug in to get an error value that is less than 0.1. Okay, so L'Hopital's rule, it's not L'Hospital's rule, okay? It's L'Hopital's rule. We can use it to determine limits of indeterminate forms. What is an indeterminate form? Do you remember? Indeterminate form is like 0 over 0 or infinity over infinity. If we're taking the limits of things, like at the very beginning when we looked at problems like this here, if I take the limit of this and I plug in 2, or I plug in infinity, I end up with things like 0 over 0 and negative infinity over infinity. If I just plugged in that kind of c value there that we're approaching, right? So when I just exactly plug in or substitute what we call kind of our c value, for both of these we get 0 over 0 and negative infinity over infinity. And it's negative because it's a negative 5 x squared. So the x is positive infinity and it's squared to give us a positive infinity, but it's times a negative, right? And then on the bottom, you'll get a positive infinity. So, but do you guys remember how I could simplify that second one?
Negative
1. It's not negative 1 for the second one.
Infinity.
Not negative infinity. We can't just like simplify the infinities over infinities. Not 0. Remember we talked about powers if I'm approaching infinity? If I'm approaching infinity and I have powers that are the same, think about your horizontal asymptotes. This would evaluate to give me what? Nope. Negative 5/3. Because you look at the coefficient in front of your highest exponent. Okay? Now, other things that we talked about, like when we were trying to simplify this, is if you ever ended up with things like this, you had to do some algebra in order to simplify it, or you like maybe had to multiply by the conjugate on the bottom and the top in order to simplify it, in order for you to like evaluate what the limit was. And then there was a few that like you couldn't actually do anything with, you couldn't do any algebra with. So there's going to be methods now that we can use in order to evaluate these a lot quicker with a lot less algebra and some quick little derivatives. Okay, so this study of kind of indeterminate forms and L'Hopital's rule is new to the AP exam as of 2017. So it hasn't shown up before then, but what that means is it most likely will have at least 1 or 2 questions on there. I can't guarantee it, but I'd have a pretty good guess that there's going to be one on there. And in this class specifically, we're going to focus on all of these forms. So if you have any of those forms, you can use L'Hopital's rule. But these other forms that are here listed below would be in Calc BC. So that's in section 7.7 that you'll do next year if you're in Calc BC next year. Okay? So we won't be talking about that in this class. Now, like I was saying, sometimes you can't actually like do any algebra to simplify these limits. Like these examples right here of cosine x minus 1 over x squared minus x and e to the x plus x over x cubed. There's nothing I can do to those to simplify them. But when I plug in 0 or I plug in infinity, I end up with infinity over infinity, or I end up with 0 over 0. Okay? But if you look at this picture here for both of them, as the limit approaches 0, there's a value there, right? There's a value. And as the limit is approaching infinity on this one, there's going to be a value there, right? So we can actually find what these evaluate to using L'Hopital's rule, which L'Hopital's rule is, if you go to the second page here, all it is if, again, you have that indeterminate form, 0 over 0, infinity over infinity, some sort of pattern like that, it could be positive, it could be negative, all you're going to do is you're going to take the derivative of the top and the derivative of the bottom, and then you are going to plug in your value again. I do not want us to get confused with, we cannot do this with quotient rule, okay? If it was just take the derivative of this fraction, we cannot just take the derivative of the top and the derivative of the bottom, okay? We still have to do low d high minus high d low over low squared. Got it? Okay, we're only doing this if the word limit is in front of it. Then we can use L'Hopital's rule, okay? Here's a nice little handy-dandy sketch of what he might have looked like. I don't actually know. And that's his name, Guillaume L'Hopital. Sometimes, okay, so if you look underneath here, it says that, like, the spelling of his name, depending on what you read, it was both L'Hopital's, like, with hospital, but then also, like, with a little accent on the O. So you'll see it both ways, but it's not El Hospital. Don't go talk to your calc professor in college and say, what's that El Hospital thing again? They're going to look at you like, man, your calc teacher didn't teach you anything. So at least go and say L'Hopital's rule. L'Hopital's, let's practice it. L'Hopital's, 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 L'Hopital's. Come on, Colton. Okay, so now in Schoology, I am going to go play you Mrs. Daughtry's finest tune of her version of this wonderful song. So, an actual example now of what this means. Again, these ones on this page you can actually do some algebra with and like maybe cancel out some like factors of stuff, but we can use L'Hopital's rule instead. But what I need you guys to show me is I need you to show me like what indeterminate form do you get when you plug it in. So like for example A, I have this function. If I plug in 2 into the top and into the bottom, I get 0 over 0, right? Yes. I think. Like on the top, you plug it in, you get 0. On the bottom, you get 0, right? So when I plug in 2, on the top and the bottom, I get 0 over 0, which means that L'Hopital's rule applies. I would like you to at least write like L dot H so that I know you're going to use L'Hopital's rule. And I would like to see that you put 0 over 0. If it says to use L'Hopital's rule, show me that you at least checked to see if you had it in an indeterminate form before you now just take the derivative. So now I can take the derivative of the top and the bottom. So the derivative of the top would be 6x minus 7 over 1. And now I can plug in 2. Plug in 2, 6 times, I was about to say 6 squared. 6 times 2 would be 12 minus 7, which is 5. So your answer for this is 5. That's it. I know, so much easier, right? So much better. Okay? L'Hopital's, yeah. All right, let's do letter C quick before we do letter B. Letter C, if I plug in -2, make sure you plug it in parentheses. Plug in -2 to the top and the bottom and see what you simplify to. You're right. We did get 0 over 0. Okay? So since I got 0 over 0, we can go ahead and take L'Hopital's rule and apply it. So on the top, I will get 3x squared plus 2x minus 8 all over, again, 3x squared plus 16x plus 20. And now I plug in -2 again. Make sure you plug it in parentheses. When you plug in -2 to the top and the bottom, I get if I plug in -2, so I get 4 times 3, which is 12, plus -4 minus 8. So I get 0, right? And then on the bottom, I also get 0. So if that happens, do it again. L'Hopital's rule again. So I got the limit as x approaches -2 of 6x plus 2 over 6x plus 16. Which, when I plug in -2 this time, you will actually get your answer. I get -10 on top and 4 on the bottom. So that gives me a total of -5/2 for my answer there. So do L'Hopital's rule as many times as you need until you stop getting 0 over 0 or some other type of indeterminate form. Okay? All right, last one that I want to do on this page is letter B. Okay? So go ahead and try out letter B for me. Be careful when you're taking the derivative of the denominator because I've got a square root there. So what are you going to have to do? You're going to have to do your power rule and chain rule on that. Okay, so try out letter B. All right, let's go through this one quick because I hear two different answers that we are getting. So when I first plug in -3, I get 0 over 0. So I can apply L'Hopital's rule. And when I take the derivative of the top, I get 1. And when I take the derivative of the bottom, I get 1/2 times x squared minus 5 to the -1/2 times 2x. Got to do that chain rule. Got to do that chain rule. So now I plug in, well, let's do a little bit of simplifying here first, right? This 1/2 and this 2 is going to go away. And then could I rewrite this as the negative exponent on top? So I'd have x squared minus 5 on top and I'd have x on the bottom. Or, I mean, you could just like straight plug it in on your calculator with the negative exponent and everything. But if this was like a non-calculator question, I'd probably do something like that to evaluate it. Because now, when I plug in -3 on top, we'd get the square root of 9 minus 5, which gives me 2. And on the bottom, I get -3. So -2/3 is your answer. Letter D, you can do it if you would like. The answer should be, if you want to go and check it later, it is 12 over -19 if you want to check to see if you get that answer. And then again, it's written here one more time. I think I've said it about 3, but do not ever just leave your answer as 0 over 0 or infinity over infinity. You have to take and use L'Hopital's rule in order to simplify it. Okay? Cool. All right, next page is going to have some trig functions on it that we could not do any other way other than knowing L'Hopital's rule. Okay, we're going to do 3 of the examples on this page. I want to start out by talking about letter C really quick. Letter C was one of those problems that was at the very beginning of this section because we actually know how to solve this already. Because if I'm approaching infinity, I look at the highest degrees on the top and the bottom, and my answer would just be those coefficients, right? So it'd be -5/3. Now, we could still also use L'Hopital's rule and figure out it's -5/3, right? But you don't have to. We can use those things that we already know and those shortcuts that we already know when we have the same coefficients, okay? All right, so letter A, let's go up to letter A. Letter A, if I start by plugging in 0 on top, 0 on bottom, what do I end up with? 0 over 0. So use L'Hopital's rule. Take the derivative of the top. Derivative of cosine is? Negative sign over 2x minus 1. And now I can go ahead and plug in 0. When I plug in 0, sine of 0 would be 0. So I get 0 over -1. And that is just 0. Okay, it is not 0 over 0. It's not an indeterminate form. So I do not continue and use L'Hopital's rule anymore. Okay, if I had 1 over 0, what if I had 1 over 0?
Undefined.
That would be undefined. We can't have that. Hint, there's one of those on your homework. Okay, so if it says 1 over 0, again, we don't use L'Hopital's rule again. We just say that it does not exist. Okay? All right, letter B. Letter B. Plug in 1 here. If I plug in 1,
0 over 0.
What is the natural log of 1?
1.
1. Wait, no.
It's 0.
Sorry, 0. Plug in 1, I get 0. Natural log of 1 is 0. 0 minus 1 plus 1, that gives me 0 as well. On top, and e to the 1 power minus e is equal to 0 as well. So I can go ahead and apply L'Hopital's rule. So the limit as x approaches 1. Derivative of natural log of x is 1 over x. Derivative of x is minus 1. And then in the denominator, derivative of e to the x is e to the x. And then don't get tricked. What's the derivative of e times x? Just e. So minus e. Now I plug in 1 again. 1 over 1 minus 1 gives me 0 over 0 again. I take the derivative again. L'Hopital's rule. Limit as x approaches 1. What's the derivative of 1 over x?
1 over 1.
Negative
It's 0.
x. 1 over x.
It's 1. It's just 1.
Pretend it's the same as like x to the negative 1, right? So move that down, subtract 1. Yes. So it's negative 1 over x squared, or negative x to the negative second power. And then that negative 1 goes away. And then in the denominator, what am I left with the derivative of the denominator? E to the x. What about the e? It's just a number, right? So it goes away. Now I plug in 1. If I plug in 1, I get negative 1 over 1.
Negative 1.
Negative 1 over, negative 1 over e to the first power. So negative 1 over e is my answer as a fraction. If I plugged it in my calculator, I'd get some sort of decimal. I'm not exactly sure what that decimal is, but either answer would be fine, fraction or decimal. Oops. Questions on that one, or feel okay? Okay, go ahead and try out letter D for me, plugging in infinity this time. What are we going to get when I plug in infinity? So when I plug in infinity, what would I get on the top? Infinity, and on the bottom we would get also infinity. So I'm going to use L'Hopital's rule, and I'm going to take the derivative of the top and of the bottom. So derivative of the top, not too bad. What's the derivative of the top?
8x minus 5.
8x minus 5. On the bottom, e to the 5x, you have to use the chain rule. So derivative of e to the 5x is... Wait, what'd you say, Olivia? E to the 5x times 5. I'm going to write it just as 5e to the 5x. Okay? And then derivative of natural log of x would be 1 over x. Okay, let's plug in infinity again. If I plug in infinity again on the top, 8 times infinity would still give me infinity. On the bottom, this first piece is going to go to what? If I have e to a power 5 times infinity, if I have e to a really, really big number, it goes to infinity. What's 1 over infinity go to?
0.
0. So infinity plus 0 is still infinity, right? Okay. Which means we have to do it again.
Let's go, guys. Locked in.
One more time, hopefully should be enough.
Will there be any times where we have to do this like a lot? 8.
So on the top you got 8. On the bottom again you'll have to do chain rule. So 5e to the 5x, derivative of that.
25e to the 5x.
25e to the 5x. And then derivative of 1 over x.
Is negative 1 over x squared.
Negative 1 over x squared. Okay, let's plug in infinity. What are we going to get here now? Well, this first piece is still going to go to infinity. This second piece is going to go to 0. But infinity minus 0 is still infinity. So we're left with 8 over infinity. Just because there's an infinity does not mean I take L'Hopital's rule and do it again. Think about, what does 8 over a really, really big number mean?
0.
0. So your answer for this one is 0. Okay? All right. That is it for the notes. Your homework is all of the odds on the 2 assignments. Okay? So you've got odds on L'Hopital's rule, and you've got odds on the linear approximation. Keys are both posted. You guys have about 25, 28 minutes to work. Okay?